let's start with what is a distributed system, and then I would. So initially, let's compare a traditional system with a distributed system. So distributed systems are mainly nothing but a collection of uh, computers that work on an internet. Your two phones are distributed because they are apart from each other. Any device your autonomous car is distributed. Even an IoT device, say that two IoT devices which work on the same internet within your home is distributed because they rely on some network or some communication system which has to get established. So any system works like that. Okay, any system that is over the network and uses a shared state of things, then it becomes distributed. So that is what is a distributed in simple terms. So which does not works on a single computer and works on a shared or over a network is called a distributed system. So how different is from a traditional versus a distributed system is that in a traditional systems, I probably, as even when I started working, even for 14 years before, I used to work on monolithic, not non-distributed mainframe systems where all your databases, your core business logics would lie in a single machine, and every request would come there. It would be read or write. It would work on the same state of the machine. So that's how a traditional system would look like, and that is how it used to be. So that's whereas your distributed is you can have your read and writes on a different database, get it replicated. So it depends on how you design your distributed system. So other thing is building a distributed system is a little complex over a traditional system. So that I want to build a system and I see that that if it is suitable to have everything in one place, then I would recommend to go in that way. Because building a distributed system would look like simple, but it would get complex and complex, more and more complex. So if you're able to build a system and very simple, and it's very simple and you can have it in one place, then always choose the traditional part of doing it. But your business is large and it would grow and it is geographically distributed, then you do not have a choice and you need to go as a distributed system. So the benefits of a distributed system is it has scalability, cost effectiveness, fault tolerance, low latency. Low latency again depends on your design of your system. So how you design, whether it wants to be low latency, high latency, it all depends on how you design your cap theorem. So the latency is completely it is not always a low latency. It can be low or it can be high. It depends on your design. So efficiency, parallelism, and sharding. So scalability is so in a traditional system, right? It was more of buying hardwares and ramping up your vertical scaling, but in a distributed system, it has both vertical and horizontal scalings, which gives you a lot of benefits. So what happens is that the initial cost may be very high in a distributed system when you do scaling, but over the period of time, due to horizontal scaling, the cost starts reducing, even when there are more customers or as your business starts growing. So that's how the scaling and the cost effectiveness reduces. Fault tolerance is so whereas in a traditional system, right, if your database goes down, your entire business comes to an halt. There is a lot of single point of failures, which is there in a traditional system. But whereas in your distributed system, your system continues to work even when there are other systems goes down. So that's how distributed systems are built to avoid single point of failure and be fault tolerant. So efficiency is that efficiency is how you break up a bigger, complex, monolithic application into smaller pieces and distribute it across. So parallelism is so you can have I probably as Hadoop your MapReduce, all these, right? All these concepts came out of distributed system because of the parallel complex nature, and it allows you parallel jobs to run on a commodity hardware. So that's where distributed system is advantage over a traditional system. And sharding of databases. So sharding is basically you have vertical sharding and horizontal sharding, where when you have large number of customers or business starts growing, a single traditional database would not be able to help you to scale efficiently. So that's where in a distributed system you start sharding. It can be regional based, or it can be range based, or algorithm based. So these concepts we would be taking up in the coming up classes. How are they done? So you saw the benefits, but there are a lot of disadvantages, and they are seems to be very as you start building.
Maybe Manoj, we can just take some questions in case there are from the previous two
Yeah.
slides. Any questions on the distributed systems and the benefits?
Yeah, if you have any questions, yeah, you can come up here.
So one question here, Manoj. So we can consider distributed system like our software is distributed among so many computers.
Yeah. So yeah.
Okay. Another question is like why would we want to make a software distributed?
Yeah, that's what I told. It's always best to have everything in one place. If your business is very small things, but once the business starts growing, right? So everywhere. So one say that even Facebook would like to have everything in one place. It becomes very easy to maintain, but it is not like that, right? So large number of customers starts coming in, and your business starts growing. A single database or single server is more prone to failure. So you distribute all the data so that at least even one of them goes down, someone is even the other one is still up and running, and you are able to efficiently distribute the data and keep it so that it allows you low latency, and it's again fault tolerance, like all these. And other thing is you cut down the cost gradually as your business grows up. So that's there are so the benefits are the real reasons why we started doing distributed systems.
Manoj, can you explain a bit on vertical and horizontal? And if I've started with vertical, if I have to switch to horizontal, say after 5 years by looking at my business, how difficult or easy would it be? And the same with vice versa, if I have to switch from horizontal to vertical or vertical to horizontal.
See, vertical scaling is very easy. It's one of the easiest way to scale up your system. Say that there is a large number of so they see vertical scaling and horizontal scaling are almost equal. Okay, so they would go on a straight line in a graph. Okay, so once you start buying hardware, it is like you're distributing, you're trying to install and things. But the real horizontal scaling where it happens is once you start building two different data centers, and then instead of pushing it in one place, you start distributing all your data into two different locations and diverting the traffic into two different places. Then it starts becoming horizontal. But when you physically look, right, you start buying hardwares, and then once you start racking it up, then you need load balancers to distribute the data, distribute your request which is coming in. So that is so the other point is that, as you asked, so how difficult is after 5 years you want to distribute? It's actually easy. The only thing is how have you designed initially? Okay, so when the database design, right, is very important, because once you start horizontal scaling, you need to think about how are I going to store the data into it. So whether I'm going to do within the database, there is vertical sharding and horizontal sharding within the database data itself. So how are we going to store that? So the complexity starts increasing once you start introducing horizontal scaling, because you need to bring in a lot of other concepts like consistent hashing, making sure that when a request comes in, it goes to the right database to get the data instead of just going randomly and telling that the user, I'm not able to find the data. So all this complexity will start coming in once you start doing an horizontal scaling. But whereas if you're done and initially if you have done an horizontal scaling, then moving to a vertical scaling is very easy, because you just need to add service and reshard. You need to rebalance all your service. That is what you need to do. But the other way is that if you're done vertical scaling, and you want to move on to horizontal scaling, you need to introduce a lot of other concepts. That's what I told. We would be speaking about those in the upcoming sessions, so that it would give you a clear picture between vertical scaling and horizontal scaling.
Sure, Manoj. That was helpful. Thank you.
The thing is, by nature itself, it's going to, because it is going to travel over the network, right? So those things are going to increase your complexity, and managing things, right? So you would start introducing a lot of components in between your distributed system, like load balancers, like API gateways, and you'll have CDNs, then you need to have logging to monitor all across your distributed system. You need to trace certain things out of that. All this is going to increase your complexity. And other thing is handling failures, right? Handling failures and troubleshooting them is going to be very difficult, because you may not know where it actually failed and which caused the failure. So that for that, you need to introduce new mechanisms. You need to maintain those mechanisms and everything. So that's going to always be challenging in a distributed system. Even today, it's very difficult to know exactly why a failure occurred and what was the reason. Say one case is that when a request comes, it may reach multiple layers and it may get lost somewhere, and your application even may not know why the request got lost. So in a distributed system, it's so complex to identify why really an issue occurred. So that's one reason. The other thing is like data security. So now, when in a traditional system, you have everything in one place and you can just simply make sure that everything is secure. But now in a distributed system, across that entire network or across within your boundary, you need to secure the data. Data logging has to be secured, because they've been pushed to different logging metrics, needs to be pushed to different databases, and it is being viewed by different dashboards, and everywhere by different users. Everywhere you need to have check and balances to make the data secure. So it becomes very complex more and more. And replication problem, so replication problem is always there. Even today, there is a lot of research done in the replication problem, because you would always have a replication lag. You cannot instantaneously replicate two databases between two different regions, and there will be always a consistency problem in that. So that's where I told you need to decide which one to pick based on whether you want availability or consistency. Based on a consistency only, everything happens, and based on availability, you can decide. So replication is always going to be a problem in your distributed system. Performance issues, like so when you had a single server, right? All the resources are going to lie in the same server. So accessing a disk or accessing database is all going to be in a single server, and you have to access them within the same shared location. But once it has become distributed, you're going to flow from one network to another network. You're going to do authentication, and then you're going to get the data and come back. And you're going to need multiple services in between to reach them. So that is always say that when you had a single server and everything accessing, you got it in 10 milliseconds. But once you start distributing, you're not going to get it in the same 10 milliseconds. There is always going to be a performance hit in that. It's going to be minor, but when you compare traditional way of designing a system over a distributed system, this will always be there. So any questions here? So can I move on to the next slide?
Yeah, I think that's fine.
Yeah. So one thing is when you start designing a distributed system, right? Probably most of today's systems are distributed by nature, but there's something called a fallacy of distributed system, which was initially proposed by Sun Microsystem in 90s itself. So there are 8 fallacies which they tell. So you should always you should always not think like the network is always reliable. So networks are never reliable, and then you should never think that when you design a system, it is always there is zero latency. So as part of the disadvantage itself, I told, right, there is going to be latencies. So the other thing is, third one is infinite of bandwidth. So you should never design a system that thinking that always it's going to be infinite bandwidth when a customer is coming. Like say that Netflix has only one bandwidth. Say that they have only one format of viewing the data, like 1080p. Then customers who are having low bandwidth of data, right, they'll not be able to view even a proper movie. So you should always think that there are customers who are having low bandwidth, there are customers who are having high bandwidth, and we should design a system saying that everyone is able to access that system. So then the other thing is I previously told there is a problem with security. So you should always think that the network is not secure. The other person is, the other application is secure, so we can be secure. It's not like when you build your application, when you build your microservice, you should make sure that within your organization, you make sure that your microservice is very secure from other microservices. And other thing is, you should never think that your topology does not change. It always relies the same. So if anyone works in SRE team, then you would understand how the network complexity increases, and always within the organization itself, the network topology changes a lot. And always, previously in a traditional system, you'll have a single admin or a couple of admins, but once it becomes distributed, right? So you're going to have a lot of admins, a lot of guys working on. So one guy, so that is always within the admin itself, there is going to be communication problems. So you should never think that there's one admin and we can always communicate to him and tell everything. So that's not going to happen. And cost of transportation, right? Say that your network cost, there are a lot of things added. So your resource cost, everything is not going to be zero. So once you start introducing distributed systems. And the other thing is, network is going to be heterogeneous and it is not going to be homogeneous in this. So you should always consider all these things when you're designing a distributed system, and never think that all these are available to you and you can simply go ahead and design a distributed system. So any question in this?
So all of them has a roundabout solutions to handle that, or
There are solutions, but you should never think that all these solutions are very viable. That's what I wanted.
so there's no 100% solution, foolproof solution for all the problems, right?
Yeah.
It's kind of they give around 70%, 80% cater to that.
Yeah. See, for latency, you cannot make latency to zero, right? I mean, at least 50 or less than 200 milliseconds, it's very difficult to make. You should make. So there are ways to do that, but the cost is going to increase. So obviously, your cost is somewhere you're going to compromise certain things. That's what it's going. As I told, the network is never going to be reliable, and always I told that you cannot have infinite. So I am in Bangalore. Even in Bangalore, I do not have a reliable network. Some days the network goes off and I need to wait for some times to come back. So that's how a distributed system itself is designed. So we we are moving to a better, but whether network, bandwidth, all these issues would go away. No, they are going to be there, and we are going to live with those issues only. Because of its nature itself.
Yeah, right. Thanks, Manoj.
Yeah. So, in a distributed system, right, there are two problems that people generally speak about. One is Byzantine problem, and there is two generals problem. I'll just speak about Byzantine problem, which would be useful when you can why they have this quorums, right? So read quorums, write quorums concept, right? That's from the Byzantine problem, like that comes up. So this is to know. So Byzantine problem is more of node-based behavior, how two nodes are behaving and how two nodes are not able to, in a distributed system, right? Two nodes in a shared state will not be able to know exactly what each other nodes are in which state. That is what. So the Byzantine problem and two general problems, right? So I would explain the Byzantine problem. So first, and then I'll tell you the two generals problem. So Byzantine problem is like there are two generals. Say that there are a couple of generals. Okay, so they are not able to. They want to attack a city, but what happens is they are not able to communicate. So what they do is they send messengers between them saying that they want to communicate, say that when we'll attack the city. But what happens is so one of the generals can get the information correctly, but the messengers who took the message and going to another general, right, saying that we on this date we would attack the city. That messenger can be malicious, or he may not even reach the general, right? So what happens in this state is that they would not even know that at what time to attack. So one will tell that we will go and attack. The other would have not even received the communication. So that's what is actually a Byzantine problem. So how does this help us? So how do we achieve this? How do we come out of this Byzantine problem? There are Byzantine algorithms that I probably later I would explain you. So in the coming up classes, how that can be done in those classes, I would explain you. So to achieve a Byzantine fault algorithms, right? So there is something called there's a formula called 3f plus 1. That is, if there are three generals and one malicious, say that there are three generals, okay, and there is one malicious thing, then there are only two honest generals. So in this state, right, the system cannot be tolerant. So to have a very good state, right, you should have more than two. So that is why in the quorum concept of Cassandra or all these non-SQL database, right, so where the read quorum or write quorum comes into place. Say that there are two malicious messengers, but a system to tolerate, right? So you should substitute that two, and so you should have at least 7 nodes. Out of that, 5 nodes should be honest. That is when we can tell that the system is tolerant over the Byzantine problem.
Manoj, one doubt.
Yeah.
3f plus 1 general means there are 3 faults or 3 actual generals and 1 malicious.
Yeah, 1 malicious.
Okay.
So if you substitute 3 in F is the malicious one. If you substitute 1, right, then it becomes
4.
3. So 4, right? So that is where the system would not be able to tolerate that. That's what they're trying to.
So if you put 1 malicious in 3f plus 1, right, it will be 3 into 1 plus 1, right? It will be 4.
Yeah, 4. It's 4.
Right.
So it is bigger than 3.
Mm-hmm.
That is one third of the thing should be it should be less than 1/3. That is when we would consider the system to tolerate. So in this, if you put 1, right,
Yes.
it becomes 4, so the system would be tolerant. But say that there are only 3 generals and one is malicious, then the system is not tolerant. That is what I want to explain. Say that there are only 3 generals.
Okay.
One is already so anything below this 3f plus 1, right? A system would not be able to tolerate.
Okay. Okay. This is the constraint to be met.
Constraint, yeah, that's the constraint. Anything below this,
Yeah, below this it goes, it will not be tolerate. Only when it goes, and F denotes a fault count. Is it right?
yeah, it's like fault count.
Yeah.
I do not have a diagram, so I want to explain it in a how actually it works in a real state. Say that you have. Can I draw in this?
In this, no, in Google Meet, I don't think so. You have option to draw. You can use one diagram. There's a tool called diagram net where you can just draw, and we can share it if you want.
Actually, there is a whiteboard.
There is a whiteboard option in more.
Okay.
How do I draw?
Whiteboard. Open a jam. In the Google Meet, there's a whiteboard.
Oh, there's a whiteboard. Okay. So where is it?
Let me try starting.
You have that after presenting, you have 3 vertical dots, right?
Yeah.
Just click on that. You have something called a whiteboard.
So this one, right?
Yeah, I think so. Yes.
Yeah. Okay. So you have something like I want to explain you. So you have a customer system, okay? Then you have an order system. So this system connects to the order, right? So this system connects to an order. Let me do this. Okay. And this connects to a payment. For now, let me keep like this. And this is an online shopping. Okay, and this connects here. And everything connects to the order system, okay? Because that's where you're going to trying to order things. See, state of all these 3 systems, right, are going to be in different states. So each of them are not going to believe each of them. So one thing is, this system can be malicious, so the payment system will always not trust this guy. Okay, and in the same way, the online shopping, right, can trust payment, but the payment system cannot trust this because you can have bots to create things, and that would make the payment, right? Then so you have roundabout that to solve that problem. But so how does the Byzantine problem works in a real-time distributed system? That's what I'm trying to explain. So that is how. So these 2 guys will not be trusting each other, and these 2 guys will not be trusting each other, and that can be say that when an online shop sends a message, someone can intrude this message and then send a different message to him, right, and get the money back. So in the same way, customer is always going to be malicious. Someone and a hacker can send and can try stealing your money or take away your order and place a different order using your credentials, right? So that's why payment system does not trust the customer, but the customer can trust this. So this is how a problem in the Byzantine, right? So each and every one has to have a proper communication in between them to execute their orders. So that is why. So in this place, it's like army, which are trying to coordinate between each other to attack the city. That's how it works.
Oh, got it. But this will satisfy 3f plus 1? No, right? there's one for
3F plus 1 is like you are having three different systems here, three different systems here, three different systems. This is not, this is like that this is a city and the army is trying to attack this city.
correct.
They're trying to coordinate with each other, but in between someone is trying to intrude and give a different message to saying that don't attack.
Okay.
Okay. But what 3F plus 1 means that even during a failed state or the system goes unbehaviorally, right? When an algorithm changes from its state to a different state, that is called Byzantine. Okay. It is not behaving it on its command. Say that the online shopping sends a message to make the payment, but it does not make the payment. It sends away to a different payment. Then that becomes a malicious behavior of the payment system. That is where we tell that at least it should be greater than 3 for a system to work correctly. So that is why I told, right, like Cassandra, where it has the default factor of replication factor should be always greater than 3. So that is all. One of the nodes behave weirdly. There are other 2 nodes which can work correctly, right? Would give you the right result.
Correct. So the majority of it's like a majority it is giving the right results and one of them is giving a failure, right?
Yeah. So that in place, that you so those,
Right.
yeah. So this is like what I'm trying to tell is, if you go to that concept, right, then you will not understand what is Byzantine. Why are they trying to do? How they achieved that state, right, is by understanding this problem. Only they moved from this. So how do you rectify this problem? That is when they come up with all these formulas like 3F plus 1. How do we mathematically solve this? Is by introducing multiple nodes, so that when you write something, make sure that you write into 3 nodes, at least one of the node. It's like Byzantine is not like something a system behaves really alone. Even if the system is not reachable or if the system crashes, at least you have 2 nodes to respond back to you to give some results which you would decide which one is the latest one and send back. Okay, so the Byzantine problem is like to make you to understand how a distributed system initially started with all these problems, and how did they move on and build products like Cassandra with the quorum of 3, all this. Why are they writing to 3 nodes? Just why not 2 or 1 node? Is it not enough? So if you understand this problem, then you will understand why they are trying to write into 3 nodes or greater than 3 nodes to achieve consistency or availability. All these, how are they addressing all those problems? So that is from this song.
Okay, got it.
Yeah. So there's one slide which so there's a 2 general problem, right? That is more like same only, but 2 generals in between, right? This is more of a node behavior. There are 2 things. One is Byzantine problem is all about how the nodes are trying to behave. The 2 general problem is it's more about how the networks are behaving. Okay, say that there are 2 generals there is general 1 and there is general 2. Okay, so they're trying to attack a city. Okay, sorry. So they're trying to attack this city. These 2 generals say that they are far away and they are not able to communicate through voice, but they need to send someone to tell that on this date we would go and attack the city. So what happens is this general 1, right? This is general 2. He sends someone to go and tell that on say that 20th June we would attack the city. But what happens is the general 1 sends the information, can reach here, and general 2 can send the information which would never even reach this one. Okay, there's another problem is that the Gender 1 sends the information, but it never even reached the Gender 2. So he is still waiting, thinking that he would be sending the information, but the Gender 1 will think that I have already sent the information. The other, so the previous one is that the General 1, right, would have sent this information to Gender 2, that he would not even know whether it reached. Until he gets a response back, he will not even know. So the state of 2 is always like, the state of 1 is always like that I have sent an information, but he has not got an information. The state of 2 is always unaware of what state 1 is thinking about. So that is because this in between, right, there is a network problem, right? So always two nodes, right, will not know each other's nodes state in a distributed system. That is why this is called two generals problem.
Okay, so is there a solution for this also when we going further?
Yeah, no, that is why you have all these TCP calls, right? So where TCP is meant when there is a packet drop.
Right.
Then you duplicately you send those packets there, and then it gets realigned. So all these problems are being addressed, but it's not always 100% guaranteed that you will always have a sure things to work. That is why. So these problems are something that if you understand, then you would be able to correlate things, why they are having, what is the reason why these systems were built like this.
Okay. Yeah. The Cassandra example you gave, that was very clear. Too general, I was thinking like whether the solutions are built at network layer or is it like
network layer. It is at the network layer. You have the TCP, then you have RPC. All these concepts came later, right? So to address all these issues only.
Okay. Right. Got it.
Yeah. So the other thing is there's one. Let me share it. So you're able to see my screen, right? You are still seeing the whiteboard, or you are able to see the?
We are seeing you are sharing some abstract, right?
Yeah. Yeah, that's so. This was in 1994, right? And Sam and Jim and Jeff. So they were part of the Sun Microsystem. So they were doing some distributed system, and they told that it's a very good. It's a short note on distributed system, which was written by these guys in 1994. So they tell about all these latency problems, memory access issues. Because in a shared system, right, say that in a NFS storage, right, you're going to access the same file or same resource or something, then two systems would not know the state of who's accessing what. So there are problems with that. Then you still have network failures, and then you have partial failures of the network, which goes and comes back. And then you have geolocation problems, right? So you have distributed systems across, and there can be any natural catastrophe which may bring down your geolocation. So all these have been addressed, but these are some of the distributed systems. When you build distributed system, right, you still need to consider you have no other choice. That's what. So say like so for partial failures, right, it's like you're calling service A, service A is calling service B, but it would have not even responded, right? Say that it would always respond with less than 200 milliseconds. For some reason, say that there is some garbage collection going on, and if your memory is huge and the garbage collection even can run for minutes, so during that time it will never even respond. So B would not even know the state of A. So during that time, it becomes a partial failure, and the network and to address, so it can be indefinitely varying. So that's why we bring in all these timeout concepts. Then all these new microservice patterns which have come, like circuit breaker. All these things are evolved out of these problems only. So if you want to study more on distributed system, then there's one good book by Martin Klippmann, design and data intensive application. So that is where even I studied and started understanding all these problems. And so he speaks very intensely about Byzantine problem, and he tells how these problems are being addressed in the databases like Cassandra, MongoDB, all these things. So that's a very good book, so which I would recommend if you're starting and if you want to really understand distributed system and its complexity. I would recommend that book. There are other couple of books, but I read that book, seems to be very good. So that book is more about databases, how in a distributed system databases work, how researches are still going on in that area. So it speaks about all that. And the other thing is, same Martin Klippmann, so he has conducted he has a lecture about distributed systems on YouTube. You can just search his name, you will get around 8 lectures on distributed system. So it's actually very good. It's a very good where he speaks very intensively about that. He's a professor from Cambridge University. So any questions?
No, my side it's clear. So this microservices architecture mostly falls into the bracket of the distributed systems, where most issues is
It falls in the distributed system because
right. When we move out from the monolith systems, you will move into microservices, and you have fault tolerance, performance issues, data replication issues, everything, right?
So that's always is going to be that. You need to always consider that.
Right.
So one thing I left in this is so in a distributed system, right? Clocks are very important because in the monolithic, it's going to be single server, single region, and you're not worried much about it, right? But in a distributed system, synchronization of clocks are very important, and you're trying to store data, or you're going to retrieve data for different analytics purposes or recommendation purposes. Then you're going to pull data across from geolocations, right? You're going to have different timings, right? So you should always maintain your servers in a single clock across the globe so that you can easily convert them. If not, you're going to run into a lot of issues. And other point is that as part of Martin's Klippmann books, he speaks very extensively about that clock synchronization problems. And it's very good if you really want to understand problems of synchronization clocks, because time is very important, right? You cannot fall back in time. It's always physically, as per physics, there's only forward in time, there's no backward in time. So maintaining your databases and maintaining a system always in forward time is very important. If not, you're going to mess up with the data, or things is going to terribly go wrong. And when you're trying to troubleshoot in a distributed environment, time plays a very important role, because you need to know when it really occurred, right? At what time, in which region. So all these conversions are very important in a distributed system to understand the complexity of time, and troubleshooting is very important in a distributed system.
Also, the database synchronization between the multiple databases, right?
So that's right. If you, I probably guess going forward, I would be speaking about synchronization clocks, logical clocks, and synchronization clocks. It's very important. Keeping track of time is very important in a distributed system, because you're going to replicate data, right?
Yeah.
You're going to store information about a customer who has done some activity, right? So it's very important to maintain time in a distributed system. So it may be any activity, right? Your Facebook timeline, because at the background, you may not know how much of data is getting collected, right? So there are a lot of metrics getting collected always, right?
Right.
How are they maintaining those metrics? So time is very important for each and every distributed system. So when you design a distributed system, always you're building something new from the scratch. Always make sure that always speak with the SRE team to make sure that so what time is maintained at the server. All these things have to be calculated as part of your design itself.
Okay, right.
So any hi Tarun, I think probably you're done the presentation.
Great, Manoj. Nice explanations, and you have also answered the queries well. So, no, just highlighting one important fact that now this was very interesting discussion on Byzantine generals problem, and this is nowadays also very important topic in blockchain, right? So we has very various applications, and one of interesting implementation or is interesting application of this theory is nowadays in cryptocurrency and blockchain as well. So maybe people can do more research on it. There are different solutions to the problems,
Yeah.
and with few assumptions about the message reliability, about detection of message delivery failures, etc. There could be different ways in which solution could be provided. So yes, this is interesting topic to learn more about it, and then you can apply it in your systems. Perfect. So
Yeah, so
any
one
other
thing is that
any other suggestions, questions no on this format of learning, and what should we do for the next time? What are the topics proposed? We can also conclude on that.
yeah, so one thing is that see all these Byzantine problem, right? So they do not apply for consensus algorithms like Raft. All these guys, right? They think that there is no Byzantine problem, and they go ahead and those algorithms think that there is no Byzantine problem, and they go. All consensus algorithms do not consider Byzantine into its factor. So I think studying that thing, right, you'll understand a lot of things around the distributed system. Yeah, I think probably I would keep on recommending Martin Klipman's book. It's really very interesting. I probably, yes, when you study that book, right, I would recommend you to not be in a hurry, because there are a lot of things there are a lot of nuance to that. I would tell that study slowly, understand each and every chapter, go slow by slow. So once you're done with that book, you'll be very good at understanding distributed systems.
Great. So what should we do for the next session next Sunday?
We should dive more on, since we started on the distributed systems, one suggestion is like take one topic or something of the, we can discuss on some highlights from that book, because that's one of a kind of a Bible on the distributed systems. Or we can go in the microservices, how do the systems are, issues are getting resolved in the microservice architecture, where the real application of the distributed systems comes into picture. Right. So I was just thinking, and that is my thoughts on whatever.
You can suggest.
Yeah, my suggestion of what I was thinking. Others can pitch in also.
Sure. Yeah, nice suggestion, and probably yes. No, you people can think about, and need not have to be immediate. It could be in few days. We can share some thoughts and suggestions, and then we can kind of take up more topics in the coming weeks. Great, great. Cool. Anything else from anyone? Okay, if nothing further, then again thanking Manoj very much for this wonderful presentation. And let's meet next session with more topics. And people can volunteer if they want to present some topic, they can also share. And also they can share some topics which which you will look forward to hear from. So both kind of proposals I will welcome, which is if someone wants to present or if someone wants to learn from others some more topics, he or she can put what topics will interest him or her, and what they consider important and they are struggling to learn. So that could be one more kind of suggestions which could be shared to me.
Yeah, so one thing is, actually, we want to learn from you all because it should be a two-way. It's not like one way. Even I may not know a lot of things. Even I'm very new to distributed systems. So it should be two ways so that we all can learn and grow as a community. That's what I and Tarun spoke, and that's why we initiated this one.
Sure. I think that's healthy discussions when we keep exchanging the points and ideas, or like real case examples where we have faced the issues and how did we solve it out on those things.
Yeah, that's right.
Sure, Manoj.
Great. Then I'll share the recording,
Yeah.
and definitely we'll discuss more about this offline, and see you then with the next session soon, and also have a nice Sunday ahead. Perfect.
Yeah. So one thing is that it doesn't need to be only from Scalar. People can join this from outside also, so that we can make it a bigger community and we can learn more out of it.
Okay. Yeah, great. This was important point I forgot. That okay, feel free to invite your colleagues, friends, whoever wants to learn and share information about system design. So just only objective and goal of these sessions are learning and sharing knowledge with each other. So yes, whoever is interested in this is welcome to participate.
Sure. Yeah, that's a good note, so that we can invite more people who are interested in learning part of it.
Yes.
Right? Sure. I'll pass on the message.
Great.
Thanks, man.
Great.
Thank you, guys. Thank you.
Thank you.
Thank you. Thanks, Tarun. Thanks, Manoj.
Thank you.
Sure. Thank you, everyone.
Thank you all. Thank you.
Thank you all.